begin. So today we're going to be going over Jeffrey's prior. I want to point out just real quickly, because I've seen his name butchered many times. Sometimes you'll see people write this. Jeffrey's is prior. And this is incorrect. So his name is actually Jeffries. It's not with an IES. I saw somebody do that once. I thought it was kind of like, just check these things. So this would go over here. And so that's the way we usually do that. Or you could say, you know, Jeffries is prior. You just say Jeffries. Or you say the Jeffries prior. Something like that. So real quickly, who's this person? Anybody know who he is? Anybody know what he does? I don't really know who he is. You know, I've read his Wikipedia page, but maybe a better question is, what's his profession? Anybody? He's knighted, so he gets the sir in front of him, so he must have done something. He's a physicist. And so a lot of statisticians, you know, back in the 40s and 50s, they weren't statisticians. There wasn't really that term. There was scientists. So, and people needed to solve all these problems. As the field grew, it became its own discipline, and people started to specialize in this. But Harold Jeffreys, he's doing a lot of statistical analyses. So he's collecting data, and he wants to do inference on parameters. He wants to learn what they are. And so he's very concerned about properties of transformations. He doesn't want to start building arbitrariness into the analysis. He wants you to make clear choices about things. So let's just go to this example. Maybe this will be a little bit more illuminating right here. So real quickly, which distribution is this? Anybody know what it's called? It's a normal. Yeah, it's a normal, and I just parameterized it funny. This is usually called mu. So I've done some sort of transformation here, and I've kind of changed the way I want to think about it. Now I know 1 over psi or mu, that shifts x. That's what's happening. But psi itself is not a shift parameter. 1 over psi is a shift parameter. So if I move mu or 1 over psi 1 increment, this distribution slides 1 increment. If I move psi 1 increment, that's going to do something different. And so that's not a linear shift parameter. It's something different. And so let's just imagine this is how we were used to thinking about things. I always think about inverse means, don't you? And so I could ask you what's the mean of this distribution, and you'd say 1 over psi. You know, probably psi inverse. You'd probably be inclined to just call it mu. But let's say I happen to be interested in psi for whatever reason. Now, probably not all that intuitive, but if we went over to the variance, I could make this argument very easily. That we don't really have a good conception of what the variance is. It's a measure of scale in some way. But let's just go to an easier parameter and say that I chose to do this, and I wanted to talk about psi rather than mu. So what's a good prior for psi? Do we know enough in class to answer that question? Let me ask you a simpler question. So this is an easier question. Which prior, bless you, for mu? Okay, constant. I kind of like this answer, so proportional to some constant, I write down 1 because it's an easy constant to multiply by. So I'm just invoking flatness over everything. And so we had an answer to this, and if you wanted to say normal, I could accept that as an answer too. Very reasonable. And so I'd probably default on this. So let's go back to this question again. What prior for psi?
Minus, let's go 1 over psi squared.
So it's going to be minus.
Also 1.
Positive.
Also 1. So we have a couple answers. Hold on. So Christina says maybe pi psi proportional to 1. Why not? So Christina likes multiplying by 1 still. And Ben has a different answer.
1 over psi squared.
1 over psi squared. So Ben has this answer. might wonder where Ben came up with that. I know his trick. So what did he do?
Jacobi, right?
Yeah, he just transformed this into that. And so let me just ask a question. So let's just call this choice 1. This is choice 2. And I'll show you what Ben did, what Christina just mentioned. We will be doing review sessions tonight and tomorrow night here in this room, 6:30. I'll show up to both of them. So Ben knows how to transform random variables. So he has a transformation of mu. So how does he end up? What's my function of mu? How do I do all of this? So what he ended up doing is he took, I'll just write down the transform. What you usually do, let's just say to transform x, where my transformation of x is gx, I'm going to call this something different, z. So let this be a random variable. Z is also a random variable. If I transform something random, it's still random. So if I want to find our PDF on Z, I need the PDF on X. So let the PDF for X be denoted, I'll write down PXX. So I'm going to be really specific about this. A lot of times I just write down P or F or something like that. I just want to be really specific about what that function is. A lot of times when we see statistical notation and everybody's running around with F's and P's or something like that, they're all different and you're supposed to know that. So I'm going to be extra careful and say this is the random variable right here. This is the argument into the function. So if I want Z right here, then what I do is I take this function for X, I plug in G inverse Z, and I should be specific about this and say this is a one-to-one function so that I can do this inversion. If I can't do this inversion, then I have to break it up into segments where you can do the inversion. Those are nasty little problems. Not too hard if you have samples, because all you do is just transform directly, but for a continuum, it'd be kind of difficult to work this thing out, possibly. And so that's my transformation rule. So that's exactly what Ben just used to invoke this. So he took 1 over phi. What's my thing right here? I'm going to take pi choice 1. I'll call this 1 and 2. So I'm going to take pi 1, and I'm going to plug in 1 over psi. And then I'm going to multiply by this Jacobian. I call it a Jacobian because I'm always thinking about the high dimensional analog, but it's just a derivative in an absolute value. And so what is this thing right here? Well, this was proportional to 1. And so this is going to be proportional to 1 times 1 over psi squared. We get Ben's answer. So, but we still have these two choices. And so let me just ask, how many of you like choice 1? There was at least one. Put them up so I can just count. I'm curious. 1, 2, take 2. How many people like choice 2? More. So 20 or so. And so let me just ask the 2 people that said that they like choice 1. Do you also like this choice?
Yes. So the thing is that regardless of how you're going to choose that, weighting everything equally, if you just have any other transform, then again, you will not have something uniform.
That's right.
So it depends on what are your parameters at the end of the day.
Let me go back to my original question. So, do you like this choice?
Yes.
You do, okay. Do you like this choice?
Yes.
You're inconsistent.
Oh.
So, you can't like both of them at the same time because they say totally different things.
No, I mean, if I'm evaluating mu at the end of, if my final interest is to find mu, then I might as well equally prioritize. have an equal priority over everything, you know?
Okay. So all I'm saying, this is all I'm going to say right here, and I get it. I know why your intuition is I kind of like this uniform thing. I want to put an equal weighting on everything, but you kind of didn't. You know, when you say I'm going to put an every equal weighting on mu right here on some transform of mu, I haven't equally weighted it at all. And so in some other transform space, you're not equally weighting. And you can't equal weight all of them simultaneously.
Yeah.
That would be really cool if you could, but it's a violation of math. So all I'm going to say is this, is that if you like this, you should also like that, because they're the same. They're equivalent to each other. So let me write it down. Pi, mu, proportional to 1 is exactly the same as pi psi proportional to 1 over psi squared. And so if you like this, you also like this. And that's what it says. And that's just math. And so 1 to 1, I give you one thing, I might dress it up a little bit differently, but it's still exactly the same thing. I can go back and forth between them. And they describe exactly the same information. And this is the question Jeffries was pondering, because it's very intuitive maybe at first to just say, well, I'll just flat prior away on everything. The question is that the right thing to do? If you did like flat prior in your original parameterization, you don't like flat prior on your transform space. So flat priors themselves are not invariant to transforms. So let me write that down. So I'll talk about a non-invariant rule. So here's a non-invariant. And I'm going to write down the transforms. Prior rule. So I'm cutting it up with a rule. Just making up this rule. It says, put uniform priors on whatever parameterization you'd like. Let's just go back to our example over here. That says if I wanted to learn about mu, I put down a uniform prior on mu. However, if I wanted to learn about psi, I put down a uniform prior on psi. Now, those two analyses will have two different results, even though they're 1 to 1 with each other. And so there's a little bit of a problem with this rule, is it made a difference which choice I decided to work with. Making it even harder, I could have said, okay, let's try to learn about sigma simultaneously. So I'm going to put flat prior on sigma. Or maybe I could have put flat prior on sigma squared, which is a different parameter. Or I could have put flat prior on 1 over sigma squared. In all of those analyses, we'll come up with different results. And so that's a little bit unsatisfying. How will they be different? They'll be different by the Jacobian factor. And so in the PDF. And we want to make sure that when we pick our transform space, we're doing it appropriately. Or we want to make sure that we have a rule that if we all follow that rule, we would come up with the same inferences. So that's what our goal is. And that's what Harold Jeffrey's goal was. He doesn't want to introduce arbitrariness to his analysis. And so he wants a rule that he can stick with so that irregardless of the parameterized space I work in, I'll get the same analysis, no matter what. So you pick whatever transform you like, I pick whatever transform I like. We follow some rule, not this one, because this would lead to different answers, but such that we would come up with the same answers. Reasonable goal, right? And so it makes you immune to picking the wrong parameterization. At least you come up with answers that are equivalent, regardless of how you do this. So let me just show you a couple things. So I would say this invariant rule is not very good and don't do it. And so It's appealing, but once you realize what transforming random variables do, you kind of uneven weight that whole space. Okay, consider the quantity. I'm going to write down I theta. This is just some parameter. Is going to be equal to minus expectation of second derivative with respect to theta, logarithm of the density function that contains theta. I'm going to say given theta, just to be real clear about all this. I'm writing e's and thetas. Let's just write it down like that. Okay, so what expectation is this? This is the expectation over x. Right here. So I'm imagining I have some model, and it looks like this. Has anybody seen this quantity before? It's the Fisher info. And it can also be written another way. Under a general regularity condition, I'll tell you what it is in a second, these will be equivalent to each other. So this is first derivative, logarithm, fx, given theta, this whole quantity squared. And it turns out those are equivalent to each other if Houdini's holds. So what I mean is we can interchange integration and derivatives. Keep in mind there's derivatives in here and integrals. So if I can exchange the order of those things, these two statements are the same. If you wanted me to prove that to you, a review session would be a good place to do that or something like that. But take a whack at it yourself. This is certainly in your inference book. So derivatives and integrals exchangeable. It's a condition that we usually have. I'm not going to say you always have this condition. So I like thinking about these two different forms a little, in different times when I'm trying to analyze what's going on. And so this is kind of interesting to me, the second derivative. And this is really the log likelihood function because I'm operating on it as a function of theta. And so what this is doing is it's looking for the curvature of the log likelihood function. So it's looking at how curved that space is. And so if it's very, very curved, we would expect, or if it's very uncurved, it's flat, we'd expect there to be a lot of variance in that distribution. And so a lot of people will use the inverse of this to estimate variances. Does anybody know what that's called? That's the Kramer-Rao bound. So that will be in your inference book as well. Sometimes I like to think about this form right here because it tells me that the quantity is positive. So I'm taking the expectation of something squared, this quantity better be positive. And the inverse of this thing is some proxy for variances. Sometimes it's not an estimation, it's exact. So lots of cool things happen with this function right here. We're going to use it entirely differently. So Bayesian uses the Fisher information sometimes to form a prior. So I'm going to show you something. This is a fact, and I'll prove this next time at the beginning of class. Here's a fact. I theta is going to be equal to I phi. And let me just write down real quickly. For our transforms, we know this. I'll say pi phi, this is phi right here, is going to be equal to pi theta. This is going to be G inverse phi, B G inverse phi theta. dphi.
Is that also phi by phi or divided?
This is dphi,
In the second term. on the right.
This.
Yeah, is it theta or phi?
theta, phi.
Okay.
So this is the density for theta, and I've plugged in my representation of theta into it.
Okay.
This is just another way of writing down theta. So I'm going to write down theta is equal to g inverse phi. So that's the transformation function. So we've wielded that thing quite a few times. So let me just write this a little bit differently. This top thing is theta. And so what we have is we have pi phi is going to be equal to pi theta d theta d phi. So that's kind of cool. Okay, so that's the relationship that we have between thetas and phis when we transform random variables. So we've now done this quite a few times. And I've been a little bit less specific in my notation right here. But this shows the relationship phi and theta have when you move between distributions. Turns out this is a fact. So I didn't finish writing right here. This is going to be, I'll write it this way just to match everything up. I phi, I theta, and this is going to be d theta d phi squared. We can prove that next time. So it's just a simple left, right hand side check. And so if you understand where this scaling factor is coming from, it's just a chain rule. It's getting rolled through everything. It's always guaranteed to be positive too. But this is a fact. So the Fisher info on phi is equal to the Fisher info on theta times this squared derivative. Okay, so we just need to do some math, go back to those forms that I wrote down and prove that. Let's not worry about the proof. You can play around with it tonight or check your textbook. It's in every Bayesian book. And we'll talk about it at the beginning of class next time. And so, turns out this almost has the same form as that. It has the same connection between these two functions with this thing, except this one is squared and that one's not squared. So we want to come up with a function that's transform invariant. That's Harold Jeffrey's goal. And he's almost got a function that always operates this way. And so, however, this function right here displays the exact same pattern. I'm going to write down 1/2 d theta d phi as this function up here. So it turns out the square root of the Fisher info has this transformation invariant property that we see when going between parameters and distributions, when we transform random variables. So all I'm saying is that if you're going to be consistent in talking about theta and phi up in this probability distribution, you better multiply by that thing. So that is the thing that carries you over to that space. So it stretches that space. Info functions square rooted have that same connection, the same representation. And so Harold Jeffrey wants to invoke this sort of thing in his rule, so it becomes automatic. And it turns out with info functions, square roots of them, you have that same pattern. And so the Bayesian does this. This is Jeffrey's prior. And if you didn't understand what I just said mathematically, we'll look at a couple examples, see what's really going on. So Jeffrey's prior. And I'll write it down like this, pi j. And I probably only use this notation throughout this lecture, just to be specific about this. Jeffrey's prior on some parameterization, I'll call it theta, is going to be proportional to I theta half power. That's it. So it's an auto rule. And it turns out this rule is transform invariant. Why is it transform invariant? Because of this right here. We haven't proven that. Just embed 2 lines of mathematics and I'll show you some chain rule next time. And so this is what the Bayesian might do if they want this sort of auto rule right here. We're going to discuss issues with this rule. What I also mean, if this was a high dimensional thing, imagine phi maybe was 2 or 3 dimensional, What I mean right here is this would be the Jacobian function, just like we do with transforms. In the half power, right here, what I mean is take a Cholesky factor. So factorize that matrix into two things that I multiply into each other, and it forms that thing. So it can be your spectral decomposition or your Cholesky factor, whichever one you like to do. And so the factor of this matrix is the high-dimensional analog. I won't be asking you to compute any of this in high D. Nice problems to do, and we'll talk about issues with this in high D and what these priors are and what they are not. Let's look at an example.
Excuse me, so here you're saying that this is transform invariant, but we still have the Jacobian. So we did reduce the squared term to a Jacobian.
This function
Yeah.
has this relationship with that function.
Okay.
This function has this relationship with this thing over here. They have the same
Right.
relationships.
Okay.
So it's transform invariant. Let me show you what I mean by it through an example. And you'll understand this just a little bit better.
For the equation, there is a negative something, I theta equals to negative something, so why we can do square root to it?
There's no negative. This is a positive quantity.
That's what.
You like this one?
Yeah.
This thing right here, what I haven't shown you is this is negative. So this is positive. You would agree? If these are equal to each other, this one's also positive. So it turns out, when I take the logarithm of this thing and I take the derivative, this expectation right here is negative. So the negative sign flips through. So good question, but it's positive.
Does it need to be a monotonic transformation?
These are one-to-ones is what I'm talking about right now.
Okay.
So one-to-ones so that I can write down G inverse. Okay? So same thing that we're always doing. It turns out you can split your function up and break it up into one-to-one sections and do all your mapping there. But if I do transformations of variables and I'm not one-to-one, I don't know if I can talk to you again after I do your transformation, or can never get back to have the same conversation. So I think for this problem, it makes sense to work with one-to-ones. Okay, here's an example. I'll tell you how I generate data. X is going to come from a normal distribution with mean mu and variance sigma squared. And I'll write this as V if you'd like. And I'll also write it as 1 over V. I've got a lot of different ways that I can express that scale term. And so sigma squared, I might call that V, I might talk about sigma, I might talk about its inverse. And I'm going to say we know this, just for the time being. So here's a question. What's Jeffrey's prior? I'll denote it pi j for V. And the answer is just do the math. So this is, again, cruise control. I know the formula, I plug everything in. There's a couple different formulas I can work with, and so you have choices. Whichever one is easier to compute is the one I would be inclined to use. So this thing right here is going to be proportional to I V half. Okay, so let's just work out what IV is. I'll work with the second derivative form. I kind of like taking the second derivative form a lot of times, so it usually starts knocking out terms. When I take a derivative, sometimes if I have these constants, they get knocked out. Don't actually like taking one derivative and then squaring my stuff a lot of times. It's usually messier. And so this is going to look like derivative, two derivatives with respect to the variance. The reason I called this variance and not sigma squared is because I have sigma squared with an operator on it, and it would look really messy. So those twos wouldn't mean the same thing. So be careful when you're playing around with sigma squareds in your formulas. Logarithm, and I always forget about log. So get that log in there. Problems always become easier when you put these logs in there too. So if you start finding yourself messing up, I'm going to assume you didn't take a log. And then I just have to write down my likelihood function. Square root 2 pi v 1/2 e to the minus 1/2 x minus mu squared over b. And you can already see that all of these constants right here, once I take the logarithm through, it's just going to be an add-on term. And then when I take a derivative, it's going to go to 0. So you never need to write down the normalizing constants. I'm just going to get rid of that. So you just need to chew on this for a couple steps. Let's just linearize it. We'll work on the derivatives in a second. And this is going to look like minus 1/2 log b minus 1/2 x minus mu squared over b. If I never tell you which log I'm taking, you can assume I use the natural logarithm. Now this doesn't look too daunting. So this is just the expectation. We'll do our first derivative. So leave one out here. This will look like plus minus 1 over b. So the derivative of log b is 1 over b minus x minus mu squared. I have a b inverse there. I pulled down my minus 1. Now I have b minus 2. I think that's right.
You drop those halves.
Yeah.
I dropped the halves, didn't I? So, you're right. Just coming back in. Did I do that one?
Yeah.
Yes. Okay, so just one more step. Derivative of this thing, so minus 1/2 b to the minus 1 plus right here 1 over v squared. And now I'll take the derivative again. Minus sign comes down, it knocks that thing out. So I'm going to get a minus sign. X minus mu squared over v cubed. Expectations easy to take. So this is going to be plus, let's just write this all down. I'll keep the minus sign out in front. And then I'll take this expectation, it's going to be 1/2 v squared. Expectation minus expectation of x minus mu squared over v cubed. What's this? Huh? It's v. It's variance. Yeah, so this is the variance right here. So we're almost there. So this is going to be equal to minus 1/2 v squared minus v squared. So this is going to be minus 1/2 v squared minus. I'll give you a hint. If this thing does not turn out positive at the end of the day, you've made a mistake. Okay, so that's that first representation. Even though I didn't use the squaring form of it, if I say they're the same, it's got to be positive. So this thing is going to have to be negative. It is. Multiplied by a negative, and it's positive. So this thing is going to look like 1/2, 1 over b squared. And so my Fisher info is that, and all I need to do to form a prior is take the half power of it. So pi Jeffreys b is proportional to 1/2 1 over b squared half power, which is proportional to 1 over b. So that's the Jeffreys prior. Now we haven't talked too much about parameterizing in terms of b. Let's talk about a different parameterization. So let's just keep this as our answer. So I'll write it down over here. So I've already got pi Jeffreys for V proportional to 1 over V. We've talked about scale invariant things. We know variance is acting as a scale, and it shows up as this 1 over scale term. So we're starting to get an intuition that we like that. Let's talk about phi. So let's now find pi phi Jeffreys. And just show that there's a connection between these two things. If you understood the math that I had written down about the relationships between the i's, you already know what will happen. Let's just work this out. And so pi, I'll just write down I phi. It's going to be equal to minus expectation, 2 derivatives on phi, logarithm, phi to the half, e to the minus phi x minus mu squared over 2. So I just reparameterize in terms of phi, and I take my derivatives there. This is going to look like minus expectation. Do our derivatives one at a time. First linearize this. So this will look like 1/2 log phi minus phi x minus mu squared over 2. First derivative is just going to be 1/2 of 1 over phi minus just a linear term there. Things get a little bit easier for us. X minus mu squared over 2. And I need to take one more derivative. Let me write that down, dt phi. And I'll finish it over here. So I'm not even thinking about anything as I do Jeffreys calculation. I'm just doing calculus. So minus expectation. And so, let's just do my derivative. So this is going to be plus 1/2. So this is going to be minus 1/2 1 over phi squared. And derivative with respect to v on the second term is 0. So I'll write down minus 0. No expectation to take. There's no x's in the equation. Notice that's negative, that's negative. This thing turned out to be positive. At least it's a sanity check. I think this might be right. And so this is going to be equal to 1/2 1 over phi squared. And so the Jeffreys prior for this is going to be proportional to 1/2 1 over phi squared, half power, which is proportional to 1 over 2. And we've seen this prior before. We've used this before. So keep in mind that was gamma 0, 0 that we had used before. What's that?
Phi is always positive.
Phi's positive, yeah, so I don't have to worry about it. But yeah, good eye, so good technical eye. It's always positive. You plug that thing in as negative and everything gets messed up in your life. That won't be a density anymore. But yeah, you're right. So let's just look at these. We have 2 priors. So Jeffrey says,
Dr. Ray, I have a question. I think you, like when you plugged in the V and the phi, aren't they reciprocals of each other? When you plugged in a V, aren't they reciprocals? So the V should now be in the numerator?
so the V should now be in the numerator. Where are we looking at?
Well, I'm confused when you said,
So the V was in the denominator and everything because it was variance.
oh, so that's left over from,
Oh
so
yeah, this is, sorry, my scribbly handwriting, breaking all the rules. This was part of this other calculation. So we
Oh,
stopped
okay.
right here.
my bad.
My bad. So let's just write down what we've got. We've got down pi phi is 1 over phi, or Jeffrey says pi v is proportional to 1 over v. Here's the whole kicker. These are the same information. This has the same information. We can verify that if I transform this into this space right here, and I know the relationships that they're just inverses of each other, I'll just move directly from one to the other. So these are equivalent to each other. Let's just verify it. Let's just show that. So I'll do my notation a little bit more carefully. So I'll just write down phi is equal to 1 over v, v is equal to 1 over phi. So this is going to be equal to pi v, but I'm going to be plugging in anywhere I see v in here, or 1 over phi. And then I've got my Jacobian term. So I just need to look at what pi v is right here, and then plug in 1 over phi in the v argument. So this thing is just 1 over phi. So that's just phi. And then I just do this right here. So this is going to be 1 over phi squared, and taking my absolute value sign. So what does this look like? This is 1 over phi. So I just transform v to do that. That's what that math shows. So this thing right here, this expression that we set with the fact, I phi is equal to I theta. I should write my halves on here. This is going to be d theta d phi. Turns out this fact that we can work out about info ends up making it so this happens every single time. So that's the whole point, that it already has this transform invariance property. It transforms in just the same way you want a distribution to transform. So it has all those same properties. So that's kind of a nice thing. You'll notice, however, that when we did this, we ended up getting something that was improper. So this is just a mathematical equation, and it structures things in just the right way. But it also leads to, in cases where you have non-compact parameters, it's going to give you something that's improper. So that's kind of interesting that that'll happen. But we've seen this prior before, we liked it. This was gamma 0, 0. What do you think this is? So Pi Jeffries from you.
So here theta is also g minus 1 of phi, right?
What's that?
Theta. Theta in the equation is also g minus 1 of phi, right? Because we're using, I sometimes feel that we're using theta and phi interchangeably.
Okay.
No, I'm just looking at the first equation. So phi is equal to phi theta.
This.
No.
This.
Yeah.
Okay.
So it's phi is equal to pi is equal to pi theta.
Would you like me to write it down like this? G inverse phi.
That's
G inverse
just
phi.
making sure that's all.
That's what it is. So that's that relationship we've learned since probability class. And so I just wrote it a little bit differently. G inverse phi is theta. And so, and this same relationship is expressed. So again, it's just chainable stuff. So what do you think this is? So all I've given you right here is just a rule. So seems to start matching some other intuitions that we have. But this is not a hard question. This is like, if I got this on an exam, well, thank you. I don't even have to think. I just calculate this thing.
Does it have to be improper?
It will be. you would probably like it to be, so that you don't put too much mass somewhere. What do you think? Well, let's just work it out. We got 5 minutes. So derivatives with respect to mu's. Logarithm, I'll get rid of all my normalizing constant stuff. 1/2 x minus mu squared, and it doesn't matter how I write this down, I'll call it b. It's just a constant. So I'm treating b as constant throughout all of this. So this will be minus expectation, and this
It's
would,
1, right?
what's that?
It's 1, right?
Close. So let's just do this. 2 derivatives. Minus 1/2 x minus mu squared over b. Let's do the first derivative right here. I'll get rid of those. My 2 comes down. And I've got chain rule. Now I do another derivative right here. And so this is a constant. So that thing just disappears. And I pick up a negative sign right here. So this is going to look like 1 over b. But b in our case is a constant, the way that we're thinking about it. And so this is proportional to any constant. And a lot of times I choose 1 for that. It's just an easier thing to write down. So it turns out that prior that we've been using, this flat prior, this thing has the right properties. It ended up just saying, okay, that's a shift parameter. I ended up getting that right just by using this default rule. And it doesn't matter which transform space I work on. So all these priors we've been playing around with so far turn out to be Jeffreys. That's pretty cool. And so I will tell you this. Jeffreys hasn't stipulated the only invariant prior rule out there. And so what I want you to do as an exercise before next time is think if you can come up with another one. I can come up with an infinite collection of them. Maybe I'll be a little bit less elusive. Turns out this is also transform invariant. So if I come up with this new function, I'll call it the Scotland function. So for theta. And this is going to be equal to expectation of, I'll write down derivative with respect to theta right here, logarithm, fx given theta, and I'll write this to the p power right here. That's the p power. I'll call this sp right here. Turns out that s p theta, the 1 over p, is also transform invariant. If you're able to fill in that one step that I've not written on the board, how the chain rule is operating, once I apply these derivatives p times, you would see this relationship. That's transform invariant as well. And so you can do this all day long. And one of my questions has always been, why did Jeffreys pick this 1? You know, and I went and I asked my Bayes instructor at the time, and she told me, well, I think that there are some arguments that can be made about admissibility. And so it turns out that in these whole class of all of these right here, you get better inferences out of the one where p is 2. And so did Jeffreys know that? I'm not sure he did know that. I know he didn't know something else about this. It turns out that in one-dimensional analyses, and all we've done on the board is just 1D analyses, these are also reference priors. And reference priors have this really neat property that it says the prior that you end up inducing is the minimal impacting prior. That is, the posterior pulls away from the prior as fast as possible. So that's as a function through the likelihood. And so I have to talk about distance functions and talk about those rates and what I mean. But under some distance function, pull back Leibler, divergence metric, it's not a distance, apologies. It turns out that these are equivalent to that formulation. Now, that's a harder problem to solve, but that's a very neat thing. So let's come back next time, discuss what this actually means, what the implications are, and discuss the higher dimensional analog of this and what properties these priors do not have. That's it for now. Thanks, Ed.